Now that we know how to measure anisotropy, let's see some data about anisotropy and what we can learn about that in terms of how much of an anisotropy is a lot and how much is not too much for both the static and the dynamic properties. So what is usually done in order to quantify this anisotropy is to measure for the static properties the Young modulus anisotropy, and this is going to be the horizontal modulus divided the vertical modulus, where the horizontal modulus is usually larger than the vertical modulus. So this ratio is going to be usually larger than 1. And for the Poisson ratio, what we do and what is most meaningful is to measure the ratio of the vertical Poisson ratio divided 1 minus the horizontal Poisson ratio. And you may wonder why we do this. Well, I hope you remember that from the linear elastic theory, this coefficient characterizes the effective lateral stress coefficient. And we haven't seen yet, but we're going to see that later, how this equation is valid for an anisotropic medium. For the isotropic case, it was just Poisson ratio divided 1 minus Poisson ratio. For the anisotropic case, now we have two different Poisson ratios. Okay, so I have here some data to share with you from different papers. And we're going to start with this publication, which let me just share very quickly with you the title and the authors. And in this publication, in figure number 8, we see results of Young modulus for shales in vertical and horizontal direction. The vertical direction are the circles, and the triangles are the ones measured in horizontal direction for different samples. And what you can see is that for the same rock, let's say for example this in red, the Haynesville shale, the horizontal Young modulus can be significantly larger than the vertical Young modulus. And this ratio characterizes how much anisotropy we have. So in this case, the anisotropy is in the order of 2, 40 divided by 20, or in this case, 60 divided by 35 or so, a little bit less than 2. There is something else very interesting to notice in this plot, and it is that this data is plotted as a function of mineral composition. And for example, what we see in shales is that as the amount of clay and kerogen, which are usually soft components of the rock, increase, these Young moduli decrease, and that also affects directly the anisotropy of the rocks. Usually when you have almost equal components of the soft and the stiff components, the anisotropy is the largest. And I have another, we're going to see the reasons for why this is the case in a little bit, but remember the horizontal Young modulus is larger than the vertical Young modulus. And I have here another case to share with you. Let me again go first to the title, the paper number, and now go to the data, where we can see quite a bit of data. This is a very nice summary of the variation of the anisotropy, static anisotropy of shale rocks as a function of the vertical Young modulus. And what we can see in this case is that the softer the rock in the vertical direction, the more anisotropy there is in these shales. And as we're going to see later, this is linked to the presence of layers of soft rock in the horizontal direction. And as the vertical Young modulus increases, and that's usually due to an increasing fraction of carbonates and quartz, the anisotropy decreases. Here we can also see this effective lateral stress coefficient and how it varies for the vertical Poisson ratio. You may notice that here that there is a good trend, but it is quite more difficult in the laboratory and in the field and everywhere to measure Poisson ratios, and there is more uncertainty in the measurement of these values. But nonetheless, we can see that, as we expect, as the Poisson ratio increases for a given formation, the effective lateral stress coefficient increases, and it depends on the anisotropy of the rock, whether that goes a little bit to higher values or to lower values. Usually rocks with high carbonate and quartz content, they have a small Poisson ratio and are closer to this region, while other rocks with more clay and kerogen locate on the right with a higher Poisson ratio and a higher effective lateral stress coefficient. Okay, the second type of quantification of anisotropy that we can do is through what are called the Thomson parameters. And the Thomson parameters are based on the ratios of characteristic velocities. For example, the first Thomson parameter epsilon characterizes the anisotropy in p waves, and this will be the horizontal p wave velocity according to what we have defined before, minus the square of the vertical p wave velocity divided 2 times the vertical p wave velocity. If you remember the definition of the stiffness coefficients, we can see that this, if we write in terms of stiffness coefficients, the mass densities are going to cancel out, and this is just going to be the difference in stiffness in horizontal and vertical direction normalized by the stiffness in vertical directions. And this is for the P wave. For the shear wave, we have the parameter gamma, which is defined as the anisotropy of the shear parameters C66 minus C44, where C66 is usually than 644, and it happens something similar to epsilon. C11 is usually larger than C33, so both epsilon and gamma are equal or larger than 1 in most cases, and the more they depart from 1, the more anisotropic the rock is. And there is one last Thomson parameter, and I told my brain to write a delta, but it wrote a gamma, and this one is defined now with inclusion of C13 and other parameters that we have seen before. Okay, so this equation is a little bit longer, and now with all of these together, I can characterize what is the anisotropy for the dynamic properties. This is very popular in the realm of seismic inversion, especially when you deal with anisotropic models, because you can clearly quantify the anisotropy in velocities. Usually in seismic, you work more with velocities rather than stiffnesses. And let me show here a quick animation, which I have right over here. And let me launch this. while I write some equations. So, okay, this is going to take some time to build. What we want to do with the Thomson parameters is that after we get to know those, it's going to be very handy in order to predict what are the velocities at an angle which does not coincide either with the horizontal or the vertical direction. So imagine this stratified geological formation with axis X and Y, where I'm going to define an angle theta measured from the vertical direction. And let me add some shading here just to make my point that these are layers and causing anisotropy, actually mechanical anisotropy in the system. So the Thomson parameters are going to help me in order to predict what is the p-wave velocity at an angle which is for theta, which is not either 0 or 90. So 0 would be the vertical velocity, 90 would be the horizontal velocity, and in between this I'm going to have the prediction from weak anisotropy that is going to be a function of this angle theta, and according to weak anisotropy theory, and this is going to be combining the Thomson parameters, is going to be that Vp at an angle theta is going to be Vp33 times a function of the Thomson coefficients and the angle delta. Okay, just one more term. And this is the equation. And as we can see, according to typical rocks, the p-wave velocity in the vertical direction is going to be lower than the p-wave velocity in horizontal direction, because these sedimentary rocks are usually softer in vertical direction. And let me show and share with you the animation I was mentioning. Let's just wait a little bit more till this builds. And this should run in just a little bit in order to visualize what is the effect of the Thomson parameters in the variation of the p waves. Till we wait for that, let's also see some cases of dynamic anisotropy. And for example, in this study, we see data in which we can observe the measurement of these Cij coefficients, in this case as a function of a peak stress, and we can see clearly how C11 is larger than C33, C66 larger than C55 or C44, and also the relationship between C12 and C13. I have another example over here of some other more recent measurements done in our laboratory, in which we also, as you can see in this example, measure C11 and C33. C11 are the filled symbols, and C33 here are the empty symbols. You can also clearly see that C11 is larger than C33, and a similar takeaway message for C66 and C44, where C66 are the field symbols and the empty symbols are C44. You may ask also, what about those red symbols? Well, these red symbols are actually igneous rocks, and these are a lot more isotropic than these other sedimentary mud rocks. Okay, let's see how this is going. Something going not working, so let me refresh this and we'll see if it runs. Okay, well, I'll come back to this, but in case it doesn't run, you can also find the link in the my geomechanics Jupyter repository, and in there I have a link to this Thomson parameter animation. Okay, so now that we have seen how to quantify this anisotropy, let's try to see some models that actually explain why a layered rock might be softer in vertical direction than in horizontal direction. And what we're going to do in order to solve that is to solve what are called the isostress and the isostrain problems for layer formations. All right. Let's divide this in two. And first of all, we're going to look for the isostress solution. This is a model that is going to help us understand the anisotropy of rocks. And this also goes by the name of the Roy's average. Okay. In this model, let's imagine that we have a rock and we have a cylindrical sample, similar to the ones that we use in our triaxial tests, which is layered and it's composed by layers which are stiff and soft. So let me add some shading here. And we're going to make the gray layers to be the soft layers and the white ones to be the stiff. So for example, over here in this layer, I'm going to have a Young modulus, which is the Young modulus of the soft layer. And here I'm going to have the Young modulus of the stiff layer. Also, this sample is going to have a certain length, which I'm going to call LT. And here I'm going to have the length of the stiff section, which characterizes how much stiff rock I have, and also the total length of the soft section. So I'm not going to write the arrows, but this is just going to be composed by the summation of the soft part and the stiff part. Okay, so let us apply a vertical loading. And if we apply such loading, like for example here, sigma v, what I'm going to have as a result is a strain in vertical direction, right? So from the definition of the Young modulus, the vertical Young modulus of this composite rock I have on the left is going to be equal to the stress applied divided the resulting strain. But notice something very important here. the strain is a result of the summation of all the strains of these layers. And therefore, the Young modulus is also going to be the result of the composite response of the entire rock. That's why I'm adding these brackets, angle brackets, which mean effective. What I'm going to do here is to solve to find an equation for what is the effective vertical Young modulus of this composite rock. And in order to do that, what I have to do is to find out first what is the effective vertical deformation, right? So this, from the equation above, the effective vertical deformation is going to be proportional to the stress applied divided the effective Young modulus. All right. What is this effective deformation? As we said before, it's going to be the summation of each of the deformations of the layers. And I'm going to divide this in two. First, I'm going to write the deformation of the stiff part. The deformation of the stiff layers is going to be proportional to the stress. Notice that the stress is the same in stiff and soft layers because they are one on top of each other. And by action-reaction, this stress should be the same in all layers. So if I want to measure the deformation of the stiff section, what I'm going to have to do is to measure the shortening of the stiff part, and the shortening is going to be sigma v divided the Young modulus of the stiff section. That's going to be the strain of the stiff section. But if I want to get the shortening in units of length, I'm going to multiply this times the length of the stiff layers. And something very similar is going to happen for the soft part. But now this is going to depend on the Young modulus of the soft part and the total length of the soft part. And last, if I want to obtain a strain, I need to divide the shortenings by the total length of the sample. So now that I have the effective strain, I can work a little bit more with this equation just to find a meaning for what we have over here. And I'm going to bring this total length inside the parentheses. So here this is just going to be sigma v divided the Young modulus of the stiff part, and this is going to be the length, total length of the stiff layers divided the total length of the sample. And by analogy, this is going to be that. But I like that you notice from here that these two parentheses, or these two terms that I have right here, are going to tell me what is the fraction of the soft part and what is the fraction of the stiff part. And this one we're just going to call it F stiff and F soft, and it's a volume fraction. How much of the stiff rock we have in comparison to the total, and how much of the soft we have in comparison with the total. Okay, so let me now use equation here. Let me call it this one 1 and equation 2. And if I use 1 and 2, what I'm going to get is that here sigma v divided the effective Young modulus is going to be equal to what I have over here, and this is going to be that sigma b divided the stiff part times the fraction of the stiff plus this times the fraction of the soft. And notice that sigma v is everywhere, so I can get rid of sigma v, and at the end of the day what I'm going to find is the equation for the effective vertical Young modulus, which is going to be what I'm writing right now, and it's a function, notice, of the Young moduli and the volume fractions of each rock. All right, so let's see the meaning now of this equation. This equation, as we said, is what is called a Roy's average, and what this equation is going to do is somehow going to penalize the soft fraction, even if it's very small because of this ratio, in the total or effective Young modulus. And if you were to plot this, what you're going to obtain is something like what I'm going to show in the following plot. All right, now this one decides to work. We'll come back to that later, we have time. Okay, here is I had a better, okay, this one is a better plot for that. This is the isostress or Roy's solution, in which we see the Young modulus predicted by such a model, just using two stiffnesses, and we see that for small fractions of the soft part, we see that the vertical Young modulus decreases considerably. And why? What's the reason? That's because the soft layers are in series with the stiff layers. And if we have a given stress, since the stress is the same in all layers, what is going to deform the most is the soft part and not that much the stiff part. So most of the deformation is going to occur in the soft layers rather than the stiff layers. And even if you have just a little bit of that, it's going to be quite soft because you're mostly deforming the soft part. And this is going to be the Roy's average, and it is what is called a lower bound for the possible value of the vertical Young modulus in a composite rock. Okay, that's for the vertical Young modulus. Let me quickly fix this so I don't have to move my equations later for the parallel modulus. All right, so now I can continue with this straight line. What I'm going to do now is we're going to develop the equation for the isostrain solution, also known as the Voigt average. Okay, in the Voigt average, we are also going to load this cylindrical rock, which is also going to be layered, and it's going to have sections of soft and stiff rock. Let me do a little bit of shading. And we'll go through the equations. Okay. So now, what we're going to apply in this case is a stress that goes in the horizontal direction. But very importantly, more than applying a stress, what we're going to fix is a strain. So that, and let me do this in 2 dimensions because in that way it's a little bit easier to explain. If this is my rock, it's a cross section. The deformation is going to be such that it's going to follow an isostrain, or the horizontal strain is going to be the same for all layers. This doesn't look like a very realistic Poisson ratio, so let me make this a little bit smaller. And the result of such isostrain is going to be something similar to what we saw for the prediction of horizontal stresses in situ with a constant tectonic strain. The larger the stiffness of the rock of a layer, the higher the reaction is going to be and the higher the stress. So in this case, the stress is not going to be constant. So again, if the white are stiff layers and the gray are soft, for a given application of a strain which is the same for all these layers, this is what the stress profile is going to look like. It's not constant. Okay, so let's see how we use now these assumptions in order to find out what the effective modulus is going to be. Okay, then the definition is going to be that similar to what we had before, the now effective horizontal Young modulus is going to be the ratio of the effective horizontal stress divided the horizontal strain, which now this horizontal strain is going to be the same in all layers. So what we're going to have to do now is to calculate what is going to be that horizontal stress. All right, so let's see. This horizontal stress, the effective value, is going to be proportional to the horizontal stress in the soft layers times the length in the soft layer, or the participation in the soft layer, and this is going to be normalized by the total length. Now I have LT, which is measured in this direction, and L soft and L stiff correspond to the lengths also in the direction of LT. So by the definition of a linear volume average, I'm just writing the equation. That volume average then is going to be how much stress I have in the soft part, which is going to be these values, times how much rock I have, plus the horizontal stress in the stiff sections, which are going to be these peaks, times the participation of the stiff rock in all of that. And now what I can do is I can use the equation I have above in order to, let's call this equation 1 and equation 2. Again, I can combine 1 and 2. And what I'm going to do is, from number 1, I'm going to solve for the effective horizontal stress. And this is going to be just the strain times the effective Young modulus in horizontal direction. And here I'm just going to bring the right hand side of equation number 2. Okay, before I do that, I'm going to calculate what those sigmas are, the sigma of the soft part and the sigma of the stiff. Notice that since the strain is the same and each of these layers, they have a Young modulus, sigma h soft is going to be proportional to EH times the Young modulus of the soft part. And we saw that before, this ratio are just the volume fractions of the soft and the volume fraction of the stiff, but I'm going to bring also the equation for the horizontal stress in the stiff layers, which is proportional to the Young modulus in the stiff layers. And that's it. This is what I get from combining 1 and 2, and also from linear elasticity. I see that now strain is the same everywhere. That's what is called the isostrain. And at the end of the day, my equation is just that the effective Young modulus is equal to a linear average of the soft and the stiff components. Notice that for a binary system like the one that we have over here, as the fraction of the soft increases, the fraction of the stiff is going to decrease. So this is actually the equation of a line, of a straight line. And the solution for that is what we see in this plot over here. This is the Isostrain equation, is the equation of a line, and predicts the Young modulus in horizontal direction, so that it decreases as a linear function of the increasing fraction of the soft part. And it is what is called an upper bound for predicting what is the maximum value of this composite rock, which we are assuming it's made out of layers of stiff and stiff and soft rock layers. And you can see that the theory gets quite close to the reality and explains very nicely why some of these rocks are anisotropic and why the horizontal Young modulus is higher than the vertical Young modulus. You can do a similar derivation for the dynamic properties and also predict these upper and lower bounds for C33, C11, C44, and C66, and so on. And you will see that also the data, especially for the dynamic part, sometimes aligns very nicely with the theory and explain the reason and the mechanism behind these anisotropic rocks. Let's see now if this is working, and then we'll close with this. Yes, it is working. So coming back then to the Thomson parameters, the Thomson parameters epsilon, gamma, and delta characterize the variation of the p wave velocities if they are in vertical direction or in horizontal direction. And as you increase the anisotropy or the epsilon, the p wave velocity in the horizontal direction increases, and now the shape of this equation is not exactly an ellipse, but is given by the equation I shared with you before, but it looks a little bit more, it looks a little bit like that. And we know that for For delta, that's going to control the shear anisotropy, and gamma is going to control the curvature of this part of the function. And I'm sorry, gamma is for the shear, so let's keep this in 0. Delta is going to control the concavity or convexity of this part of the curve. So it is not a perfect ellipse. All right, so I believe this is everything for this lecture. I'd like to remind that in other videos, and when we get to incorporate pore elasticity, we'll come back to this anisotropic model in order to build an anisotropic one-dimensional mechanical earth model.